All right, improper integrals. One thing I'll point out about improper integrals is it's not a method of integration. It's not like u sub or integration by parts or partial fractions where you're trying to do this thing to the integral to be able to anti-differentiate or integrate it. It's just the type of integral we have. We're still going to use the same methods of integration, anti-power rule, u substitution, integration by parts, etc. There's just something else you have to consider now. So let's look at kind of this first very, very classic example. You probably did this one in class, but it's worth seeing again. So we're first going to look at the integral from 1 to infinity of 1 over x dx. And the idea here is that, I mean, as the integral would suggest, we're trying to find the area under the curve from x equals 1 to all the way forever and ever and ever to the right. So it's kind of looking like this. Here's your function, 1 over x. Or I should say, here's part of your function, 1 over x, because technically it's down here as well, but I don't really care about that part right now. And we're trying to figure out how much area is under this curve, starting at x equals 1 and going all the way forever and ever and ever. So how do we compute this when x is going to infinity? Well, we're not going to deal with the infinity, essentially. We are, but we're going to pretend like we aren't for a second. So here's the idea. Instead, calculate a different integral. We're going to calculate something that looks the same, except we're going to give ourselves a stopping place. So we're going to say, well, we're still going to start at 1, but now we're going to stop at, say, b. And we're going to find that integral first. So we're going to find the integral from 1 to b of 1 over x dx. Okay, well, that's not too terrible. We know how to integrate 1 over x. It's going to be the natural log of the absolute value of x evaluated from 1 to b, which is then, now I'm going to point out here that the way I've drawn this, and certainly the way it's meant to be, b is a positive number. So when I take the natural log of b, I don't really need to write the absolute value because the absolute value of b is just b. Minus the natural log of 1, natural log of 1 is 0. So whatever b is, the area under this curve from 1 to b is exactly the natural log of b. Some positive number. But now, to look back at this and actually figure out what this improper integral might be, we're just going to take this whole expression and what are we going to let b do? B is going to go that way, all the way to, I shouldn't say 2 because you never get to infinity, all the way in the direction of infinity. So b is going to infinity. So to find our actual integral here, the integral from, I feel like one second, let me move things around slightly here. Sorry. This little knobby thing is always in the way. Okay, that's better. All right. So, I should turn on this light too. That might make it easy. Yeah, that's way better. Oh, yeah. So to find the integral from 1 to infinity of 1 over x dx, we're going to take this integral we just did, but we're going to do the limit as b goes to infinity of that integral from 1 to b. And then normally you would start there and then write all this work. We already did all this work, so let's just write the conclusion here. That's going to be the limit as b goes to infinity of the natural log of b. And even though the natural log of b gets big really, really slowly, it does keep getting bigger and bigger and bigger, right? It never like levels off or turns around. The natural log of b function goes to infinity as b is going to infinity. So this is going to be infinite. That's an infinite amount of area under that curve. So what do we say when the area is infinite, or if this limit doesn't exist, which this limit doesn't exist, right? Infinity is not a real number. This limit doesn't exist. We just like to say more about it. We know it's infinity here. What we say is the integral from 1 to infinity of 1 over x dx diverges. Because that integral is not equal to some finite number. That limit is not finite and real. Yeah. Definitely should ask questions if you have them, but we're going to do some more examples. All right, let's look at the next. We'll look at the other kind of classic example, which is the same sort of thing, except now our function is going to be 1 over x squared, which you might have already seen. Again, worth seeing again. So now we're going to look at the integral from 1 to infinity of 1 over x squared. And I'm going to draw the picture as well. It's going to look pretty much the same because I'm not that great at drawing, but you might recognize that 1 over x squared gets smaller faster. I'll try to indicate that here. It's, I don't know. Yeah, I mean, okay, but it does never get to 0, so be careful with my picture there. So now we're looking at that area. And again, we're going to do the same idea. To find this integral, we're going to write the integral from 1 to infinity as the integral from 1 to b. Instead of writing 1 over x squared, let's do ourselves a favor and write it in a way that's easier to anti-differentiate. So I'm going to rewrite 1 over x squared as x to the minus 2. But that's not equal to that. So I want to point here, these aren't equal yet, right? That integral is not equal to that integral. This is equal to that if I let b go to infinity, or if I take the limit as b approaches infinity of that integral. And then when I do this, I pretty much ignore the limit the whole time. I'm not going to look at the limit part until the very, very end of the process. So until the end, I'm just writing the limit and dealing with the integral. So I've got the limit as b goes to infinity, and then the integral here, well, the antiderivative of x to the negative 2 is x to the negative 1 divided by negative 1, evaluated from 1 to b. When I have infinities, I really don't like negative powers. Like I would find it more difficult to deal with this as divided by negative 1, same as multiplying by negative 1, as like negative b to the negative 1 minus negative 1 to the negative 1. I don't like that. Here's what I would rather write. I'd rather use a positive power. It just makes it easier for everyone to see what's happening. So equivalently, we can write this as the limit as b goes to infinity of negative 1 over b. And this here we can write it as plus 1 over 1, which is just 1. And now, at least for me, it's easier to distinguish or determine, oh yeah, as b is going to infinity, 1 over b is going to go to 0. It's going to get smaller and smaller and smaller. So this part goes to 0. The whole limit equals 0 plus 1. And since the limit here is equal to a finite real number, we say that this integral converges. And we say that it converges to that value. So you can either write, it's easier to write this, the integral from 1 to infinity of 1 over x squared dx is equal to 1. And when we say that, the words we're not always writing or saying, but we should be thinking is, this means the integral from 1 to infinity of 1 over x squared dx converges. And it converges to 1. So saying this is really saying all of that. When it's an improper integral, if it's equal to a number, you're always saying, oh, that integral that's improper is convergent, and it converges to the value that we found that it was equal to. Okay. Look at my examples here. What else have I got going on here? There's plenty of things. What is that other paper? I think I hid something for myself, as I usually do. Yeah, sorry, it's in my other notes. I'll grab it. There's something else I wanted to mention here. No, I guess I'm good. Okay. I know what it is. All right, let's look at another example. We'll kind of talk about some stuff. So let's say we want to look at the integral from negative infinity to 1 of 4 over 1 plus x squared dx. And have both classes, has Dadella's class talked about improper integrals? Has Karana's class talked about it yet? Or Dr. Burke, right? She's the other, yeah, okay. How do I say this the right way? Did either of them talk about improper integrals that didn't have infinity or negative infinity? Like improper integrals where the function was undefined somewhere. Okay, good. That is a thing that sometimes people talk about in the 17 series, but sometimes most of you get skipped over. So if either of your teachers, in fact, I'll just point one. So like just for example, we're not going to do this one unless we need to later on. But if someone gives you something like the integral of, say, the integral from, let's make it easy, from 0 to 4 of 1 over the square root of x. This integral is improper, not because there's infinity or a negative infinity, but because that function, 1 over the square root of x, is undefined at 0. So this is improper. It's these ones over here, this is usually called a type 1 improper integral, and these ones over here are called type 2. But again, if you're not doing it in class, we shouldn't spend our time doing it. That said, go ahead. Correct.
He did do something.
All right, then we're gonna do it. We'll get there. So I just want to point out what I usually like to say. What makes an integral improper is you have some sort of problem. We have an issue, and either your issue is infinity or negative infinity. Infinity is always a problem, and negative infinity is always a problem. You always have to deal with it. The other kind of issue or problem we have to deal with is that sometimes one of your limits of integration, or sometimes even worse, a point in between your limits of integration, makes your function undefined. That is also a problem that we'll have to deal with. We'll come back to this problem in a little bit here. But yes, yeah. So here, infinity is a problem, negative infinity is a problem. So we always replace the problems with a letter. It's fairly standard to replace a lower limit with an A and an upper limit with a B. But you can literally use any letter you want except for ones you've already used, like X. So don't use X if you're already using X. But A and B are pretty standard. So we're going to rewrite this as the limit as a approaches negative infinity of the integral from a to 1 of 4 over 1 plus x squared. And I should have done myself a favor. I should have pulled that 4 out in front. I should have written this as the limit as a approaches negative infinity of 4 times the integral from a to 1 of 1 over 1 plus x squared. Because then it's much, much easier, in my opinion, to see that the integral of 1 over 1 plus x squared is good old arctangent of x. And that is just something we have to know. So this is going to be equal to, again, still just writing the limit every time. The limit is a goes to negative infinity of 4 times the integral of this is the arctangent of x evaluated between a and b, or a and 1, I should say. Now we're going to plug in our limits of integration, which is different than taking the limit. Unfortunately, they have the same word used there. So then we're going to write this as the limit as a approaches negative infinity, 4 times the arctangent of 1 minus 4 times the arctangent of a. Okay. What's the arctangent of 1? What is the arctangent function in general? So when I think about the arctangent function, it's the function that kind of undoes what tangent does. So here's something I would say, just to kind of, I would say the following. So I know that tangent, let me make up something here. Sure. Tangent of pi over 3 is equal to the square root of 3. You can find that on the unit circle. That's equivalent to saying the arctangent of root 3 is equal to pi over 3. So just like inverse functions do, this inverse function, right? Because also people, I like to call arctangent because it's less confusing, but it's also the same as the inverse tangent. The inverse function interchanges the relationship between input and output. So tangent of an angle equals a number, arctangent of that number equals the angle. Or as I would read it, when I read arctangent of root 3, I'm really asking myself, what angle do I take tangent of to get root 3? Oh, pi over 3. So over here, what angle do you take tangent of to get 1? 45 degrees, pi over 4. So that's going to be pi over 4. Okay, here's the hard. So you might ask, why did you spend so much time on that part without dealing with this other part yet that might be infinity? You might make this not even matter at all. Well, it's not going to be infinity over here. So this is one that's kind of funky, but the limit as you either go to infinity or negative infinity of arctangent is pi over 2 or negative pi over 2. And the way you get that is by looking at the graph of the arctangent. So instead of me drawing it terribly, let me graph it for you on Desmos. Because I could try to squeeze it in there, but sure. I gotta this is where I wish I could see what I'm doing over here. Okay, so I'm gonna graph tangent for you first. And as you might remember, tangent's kind of terrible. There's a lot of it. And you can't really invert that function because it's not a one-to-one function, right? It's got the same y value for many, many, many different x values. So what do? We restrict that function. We say we want to limit this to just a domain between negative pi over 2 and pi over 2. Oh, come on. There we go. Just one nice restricted interval of tangent that gives you the whole gamut of y values and no repeats. And then if you invert that, you get the reflection across the line y equals x, which is going to look like, I'm just going to use the arctangent function, y equal to the arc tangent of x. Those are inverse functions. And if you go way, way, way to the right, just like your vertical asymptote for this red function is x equals pi over 2, this horizontal asymptote for this blue function is y equals pi over 2. And if you go to negative infinity, the horizontal asymptote is y equal to negative pi over 2. So that's why the limit is equal to negative pi over 2 in this case, because as you go way, way, way to the left, as x goes to negative infinity, the y values are getting closer and closer and closer to negative pi over 2. And in my opinion, this is maybe not the only way to know this, but definitely the best way to know this is to know the graph of the arctangent function. So what that means for us is, is that the limit as a goes to negative infinity of the arctangent of a is going to be negative pi over 2. So then we're left with 4 times pi over 4, which is pi, minus a minus is plus 4 times pi over 2, which is 2 pi. So we end up getting an answer of 3 pi. Neat. And again, what does that mean? It means this improper integral converges, and it converges to 3 pi. I don't know why I boxed the pi and not the 3. That seems really, really weird. Let's try that again, 3 pi. We want all of that answer, not just the pi part. Sorry. So, infinity, negative infinity, always a problem. Always have to replace them with a or b or whatever. So then, yeah, let me look here. I think I know what's coming next. Yeah. So then what happens if you have both of them? What if you have, say, the integral from negative infinity to infinity of, do I want to do that one? Sure, let's do this one. 6x to the 5th times e to the negative x to the 6th. Yeah, that seems terrible. So here's what you can't do. You can't replace negative infinity and infinity with the same letter or opposite letters. So don't write this next part down. We can't do this. We can't say that we're going to have, say, like the limit as b goes to infinity of the integral from negative b to b of the same thing. That doesn't work, unfortunately. And the reason it doesn't work is because you don't know if you're going to infinity and negative infinity at the same rate, essentially, is kind of the idea, or at least how we justify to ourselves that we don't get to do this. Here's what I want to say. For any improper integral, you can only deal with one problem at a time. And each infinity is its own problem. You can't deal with both of those at one time, so we have to deal with them separately, meaning we have to break up an integral. If your integral has 2 or more problems, you have to break it up so that your separate integrals each only have one issue to deal with. So here, we're going to break this up wherever we want. 0 is the natural choice, but you could really pick anything. But we're going to break it up at 0. So we're going to write this as the integral from negative infinity to 0 of 6x to the 5th e to the negative x to the 6th dx plus the integral from 0 to infinity of 6x to the 5th times e to the negative x to the 6th. And then we're going to write each of those as their own limits with different letters. So this first one is going to be the limit as a goes to negative infinity of the integral from a to 0 of the same function, plus the limit as b goes to infinity of the integral from 0 to b of the same function. And now we're just going to do each of them separately. Well, I should say, we're going to do one of them. And if it converges, then we're going to do the other one. And if that one also converges, then they're both going to converge and the whole thing's going to converge to whatever they add up to. But if you do one of them and it diverges, you're done. The whole thing diverges. You don't have to do the other one. You don't have to do the other one unless someone wants to ask you a very specific question about the way in which it diverges, but we're not going to concern ourselves too much with that. So they both look pretty much the same. I don't want to like write out all this stuff for all the steps every time. So what I'm going to do on the sides, I'm just going to do the indefinite integral so I can just say what each of these are going to equal to. So off on the side here, I'm just going to do the indefinite integral of 6x to the fifth e to the negative x to the sixth, which I hope is screaming a u substitution to you. There is a very, very obvious choice for u. You can either pick x to the sixth or negative x to the sixth. If I have a choice, I usually like to pick the entire exponent or thing inside the root or whatever it is. So I'm going to pick u equal to negative x to the sixth. My du is going to be negative 6x to the fifth dx. So I'm going to have negative du equal to positive 6x to the fifth dx. So when I rewrite my integral, my 6x to the fifth times dx is going to be a negative, which I'm going to put out in front, times du. There's my 6x to the fifth times dx getting replaced by negative du. And then the remaining e to the negative x to the sixth is going to be e to the u. And then the rest of this is easy. It's going to equal negative v. So I want to point out here, sometimes people do a u sub and then they kind of forget to do the integration. And part of it might be examples like this that look like I'm not doing anything. But we are taking the antiderivative of e to the u. We happen to also get e to the u. But just remember, right, with the u substitution, you still have to do the antiderivative. I'm not, yeah, no, I don't. I don't usually write a plus c over here because like this is just my own side work. You don't need the plus c really. So it's going to be negative e to the negative x to the sixth. Great. Sorry, it's a little low there, I know. So now, for this part here, I can say that's going to equal, I'm doing these separately. Yeah, that's fine. So for this left-hand side, this is going to equal the left-hand piece, I guess. The limit as a goes to negative infinity. I've already done all the work. So I'm just going to rewrite the integral of this as negative e to the negative x to the sixth, evaluated from a to 0. And yeah. So I'm going to plug in 0 first. Let me get the limit as a goes to negative infinity of negative e to the 0 minus, instead of writing negative e to the negative x to the sixth, I would really rather write negative 1 over e to the positive a to the sixth. I know I said x before, I meant to say a. Right? That's the same as negative e to the negative a to the sixth. But again, I find it extremely convenient and helpful to think of my exponent as a positive, or not to think of, to write my exponent in a way that I know it's going to be positive when I plug in whatever a is approaching. And that's what I did here, because I know now if a is going to negative infinity to the sixth power, is that going to be positive or negative? Let's see, a negative times a negative times a negative times a negative. A negative times itself 6 times is going to be a positive number. So here, this a to the sixth is really going to infinity. E to the infinity is really, really big. And 1 over that is really, really small. That's going to 0. Interesting. Sorry, I'm just... Okay, here's my issue. Here, let me explain to you why I'm pausing for a moment here. I know this some no. Oh no, I see. I'm not, yeah. Okay, good. I figured it out. So I was concerned for a second because I saw this was going to come out negative. And for a moment, I thought my function was always positive. It's not, right? 6x to the fifth is definitely negative if x is negative. But I was worried that I had an always positive function and my area was negative. That's a telltale mistake, but I didn't make a mistake. I just was thinking too hard. So then we're going to get negative 1 here. We're not done. We did half of it. But the other half is going to be pretty much the same. So the other half is going to be, so for this one here, it's going to be the limit as b goes to infinity of negative e to the negative x to the sixth, evaluated from 0 to b. Be careful, make your b's look different than your sixes. That's going to be the limit as b goes to infinity of, plugging in the b, I'm going to write negative e to the negative b to the sixth minus negative e to the negative 0 to the sixth is just 0. And then rewriting it, I've got the limit as b goes to infinity of negative 1 over e to the b to the sixth plus 1. If you're okay with saying e to the negative infinity is 0, great. I just find it less, it just makes less sense in my head. Like I know that e to a big number is a big number and 1 over a big number goes to 0. But for some reason, thinking about e to the negative infinity, I have to like think about the graph of e to the x, and then I know that if I go that way, it gets really close to 0, and that's just more thinking than I want to do. But if you're okay with that, it's totally fine to just be like, yeah, I know I'm going to have e to the negative infinity, and that's going to go to 0. So you don't have to do all the same things I'm doing. I'm just telling you how I'm thinking of it. That's getting really big, so this whole fraction is getting really small. So I'm going to end up with 1, which means my overall integral converges to 0, which always feels like a letdown, but it is the answer here. So this integral converges to 0, which I should write somewhere. So yes, converges to negative 1 plus 1, which is 0. Which shouldn't be terribly surprising because 6x to the fifth times e to the negative x to the sixth is an odd function. And you integrated this odd function from negative infinity to infinity, essentially the same positive and negative thing, so we got 0. I want to caution you. It's not always true. What do I mean by that? Let's look at one more example. Let's say I wanted to find the integral from negative infinity to infinity of x cubed dx. Well, at least graphically, you would imagine that these areas would cancel out and you'd get 0. And gosh, I wish that were true because it just feels like it should be true, but it's not. So what happens here is if you break this up, if you write it as the integral from negative infinity to 0 of x cubed dx plus the integral from 0 to infinity of x cubed dx. And let's just deal with this one first. So this one we're going to rewrite as the limit as b approaches infinity of the, integral from 0 to b of x cubed dx. We're going to integrate that after we write the limit. We're going to get x to the fourth over 4 from 0 to b. We're going to plug in, we're going to get the limit. I should say we're going to plug in the limits of integration, not the limit part yet. I know, terrible language. We're plugging in the limits of integration. We're getting b to the fourth over 4 minus 0 to the fourth over 4. And now as b goes to infinity, b to the fourth is going to get infinitely large. So this right-hand piece of my integral diverges to infinity. And really, that's where we should end this conversation. We say, cool, one part diverges, the whole thing diverges, we're done. So the whole integral does diverge. Now, if you want to say more, or at least think more, I will point out the other half of this does diverge to negative infinity. So it should be noted here, the integral from negative infinity to 0 of x cubed dx diverges to negative infinity. And the issue here, or an issue here, is that negative infinity plus infinity could be anything. It's one of those indeterminate forms, like 0 divided by 0 or infinity divided by infinity, where we actually cannot determine the value, even though the graph would make us think, and seems reasonable to think that the area should cancel out and you get 0. We don't have the math to say that. So I'm going to say it again. Even though I would love to say this integral is 0, once one part diverges, you're done, the whole thing diverges. I will say one more thing. We can't say what this thing diverges to. We don't know if it's diverging to infinity or negative infinity or something else. So we can only say it diverges. We cannot say if it's getting really, really positively big or negatively big or somewhere in between. Which, yeah, I know feels to me always like a disappointment, but that's what we got. Ooh, light's bright. I'm trying to stay out of the way of that light, but it feels like it's coming over this way. Let's see. Cool. Oh yeah, let's do one more. Okay, one more, and then we'll come back to that other one. So let's say we want to find, yeah, sure, we got room. The integral from e squared to infinity of 1 over x natural log of x. And just so we're being extra careful here, this function is undefined some places. What's one value of x that would not be okay to have? 0, right? Because 0 dividing by 0 is a problem, right? The function is undefined. What's another value of x that's a problem? Ooh, natural log of 1 would be a problem because natural log of 1 is 0 as well. So if this integral was like from 0 to infinity, it would be really, really stupid because you'd have to break it up from 0 to something between from like 0 to 1/2 and 1/2 to 1 and 1 to something and then something to infinity. You have to break it up into like 4 different integrals because there's 3 problems to deal with or something like that. It's really dumb if it's that way. Luckily, our interval doesn't include 0 and 1, so we're good. So we're just going to rewrite this as the limit as b goes to infinity of the integral from e squared to b of 1 over x natural log of x. Okay, so this integral is going to require u substitution. I really, really, really don't want to write this integral with these limits of integration and this limit while I'm doing anything other than just something that's very direct. So I would highly recommend when you have all this machinery here to take care of and your integration process is a little more complicated, like a u sub or integration by parts or partial fractions, to do that work on the side. To say, hey, cool, I can do this indefinite integral of 1 over x natural log of x on the side here. And do my usual u sub, well, do the u sub here, which is going to be u equal to the natural log of x. And my du is going to be 1 over x dx. So this is going to end up equaling the integral of, let's see, my 1 over x dx becomes my du. And then I'm left with a 1 over natural log of x, which is a 1 over u. And then we integrate. We get the natural log of the absolute value of u, which then is the natural log of the absolute value of the natural log of x. Cool. So then we did all that work on the side so that we can then go back here and say, great, we've got the limit as b goes to infinity of the antiderivative of this is the natural log of the absolute value of the natural log of x evaluated from e squared to b. We then plug those in. We get the limit as b goes to infinity of the natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of e squared. And even though it's super duper slow, natural log of b gets infinitely large, and the natural log of something that gets infinitely large also gets infinitely large. So this does go to infinity. I don't care what that goes to. It's like, I don't know, natural log of 2 or something. Infinity minus natural log of 2 is still infinity. So this does diverge to infinity. If you have a moment, I would highly encourage you to graph natural log of x on Desmos and see what it looks like. It's flat. It's not flat, but it's just growing so slowly that it looks like it's a horizontal line, but it's not. If you Right. I think I read somewhere like if you like let every second that has passed since the beginning of time and that was like your x value for the natural log of the natural log of x function, the output would be something like 40. Like the natural log of the natural log of every second since the dawn of time is about 40 because it's just so slow. All right, let's look at some of the other types of improper integrals. Let me go back to that one I started with way over here. Where did I write you? It was like from 0 to 4 of 1 over the square root of x, I think. Yeah, there we go. Yep, exactly. Well, let me sorry, I'm trying to get all my papers out of order here. So let's look at some type 2 improper integrals. So again, type 1 means you've got infinity or negative infinity or both. Type 2 means the function. So type 2 improper integral. So something like the integral from a to b of f of x dx. What makes it a type 2 improper integral is that f of x is undefined somewhere on the interval. If you're lucky, it's going to be at one of the endpoints. If you're unlucky, it's somewhere in the middle, which means you're going to have to break it up, which always feels terrible. But let's look at this first one we've got here. It's the integral from 7, from 0 to 4 of 1 over the square root of x dx. And this function is undefined at 0. So we have to replace the problem, right? It's always dealing with the problems, whether they're infinities or places where it's undefined. every problem value gets replaced with an a or a b. So we're going to rewrite this as the integral from a to 4. And let's go ahead and rewrite the function. Instead of writing it as 1 over root x, let's write it as x to the negative 1/2. And then we're going to take the limit as a approaches 0. I'll say one more thing here. Our interval is between 0 and 4. If we're between 0 and 4, what side of 4 do we have to... Whoa. If we're between 0 and 4, what side of 0 do we have to be on? We're on the right side of 0, right? We're between 0 and 4. We're numbers that are bigger than 0 and smaller than 4. We're on the right side of 0. So we're approaching 0 from the right. This doesn't usually matter too much, but it does actually matter. Like if you don't write that plus sign, you're still going to end up getting the right answer probably at the end. But it's really important that we're approaching 0 from the right because this function isn't defined on the other side of 0. Square root of a negative number, no dice. So it is important. And what always ends up happening is if it's a lower thing you're always replacing it from the right because you're always bigger than your smallest value. If it's an upper thing you're replacing, you're always approaching it from the left because you're always smaller than your biggest value. So then, usual process. We get the limit as a approaches 0 from the right. We anti-differentiate this. We get x to the 1/2 power divided by 1/2, evaluated from a to 4. We simplify and plug in our limits of integration. So it's going to be limit as a approaches 0 from the right. Divided by 1/2 is like multiplying by 2. So I'm going to get 2 times 4 to the 1/2 minus 2 times a to the 1/2. And then we plug in 0 for a, so we get 2 times the square root of 4 minus 2 times the square root of 0. Square root of 0 is 0, so this thing definitely converges. So we get 2 times 2 plus u minus 0 is equal to 4. So this integral from 0 to 4 of 1 over the square root of x dx converges to 4. Here's what I would say in general. Most of these types of improper integrals are usually improper because of some sort of division by 0. There's one exception, we'll address that in a minute. But usually it's because you're dividing by 0 in some terrible way. And so here's what's usually going to happen. If your integral makes you go from x to a negative power to x to a positive power, well, that division by 0, right? Because 0 to a negative power is really like 1 over 0 to that power. That's like dividing by 0. That 0 to a negative power being undefined, becoming 0 to a positive power, which is just nice 0, usually is going to converge. Whereas if you do the integration and you still have a negative power, that 0 to a negative power is still going to be giving you something that's divergent. So that's something just to look out for. Again, you don't have to be super aware of that, but it's just something I've noticed and I wanted to point out. Let's look at another example to kind of emphasize that. So let's say we wanted to find the integral from, I didn't even think about this one. Let's go from, sure. Sorry, I have to think. Let's go from 1 to 7 of 4 over x minus 7 cubed. Okay, I think the problem's obvious here. The problem is 7. Any other value is totally fine, but 7 is an issue. So we're going to rewrite this as the limit as b approaches 7 of the integral from 1 to b of, again, let's rewrite our integral and make it easier to integrate. 4 times x minus 7 to the negative 3rd power. And yes, we're approaching 7 from the left-hand side because we're between 1 and 7. So we're left of 7 or less than 7. You could do a u sub here. I don't really think you need to, right? We know that the integral of x to the negative 3rd is x to the negative 2nd divided by negative 2. This minus 7 doesn't really change anything. So, or if you did the u sub, u would equal x minus 7 and d would be just dx. So again, if your u is x plus a number or x minus a number, you can kind of get away without doing it. So let's just not. Let's say we have the limit as b approaches 7 from the left. The 4 hangs out. The antiderivative of x minus 7 to the negative 3rd is x minus 7 to the negative 2nd divided by negative 2. Evaluated from 1 to b. And now, just like before, I like my powers to be positive. I just find it easier to think about what's going on. 4 divided by negative 2 is negative 2. So right, this is the limit as b approaches 7 from the left of -2 times x minus 7 to the negative second is 1 over x minus 7 squared. Yes, I know I could have put the -2 on top. I just didn't. From 1 to b. Now we're going to plug in. We're going to get the limit as b approaches 7 from the left of -2 over b minus 7 squared minus -2 over 1 minus 7 squared. And right here, that's where we're going to have a problem. Because if you plug in 7, 7 minus 7 is 0, 0 squared is 0, and division by 0 is undefined. So this definitely is diverging. Specifically here, you have a negative number over a positive number, so it's diverging to negative infinity. Don't really care that much, but negative infinity plus, I don't care, plus 2 over 36. So this integral from 1 to 7 of 4 over x minus 7 cubed diverges to negative infinity. Here we saw the thing I just said, where our problem was that we had a 0 to a negative power, right? When you plug in 7, 7 minus 7 is 0 to a negative power. And when you integrated, you were still getting 0 to a negative power, which is like dividing by 0. So, yeah. What else do I have here? Is there anything else exciting? Oh, I know what we should do. Yeah, we should do that. I'm pretty sure. So let's say we have, yeah. Let's say we want to find the integral from 0 to infinity of x squared times e to the negative x. Okay, what method of integration do we have to use here? I mean, okay, I'm getting ahead of myself. I should probably start by writing a limit first. So really, we should write this as limit as b approaches infinity of the integral from 0 to b of x squared times e to the negative x. People sometimes ask, shouldn't we write like as b approaches infinity from the left? And the answer is no. You can't approach infinity from the right. You can only approach infinity from the left. You can only approach negative infinity from the right. So you don't need to say which side you're approaching either infinity from. So we want to integrate that. This is definitely integration by parts. And again, I don't want to do the integration by parts and carry all of this stuff with me. So on the side here, we're going to do integration by parts. I don't remember if I talked about this class. Did I talk about tabular integration? I think I might have mentioned it a little bit. Okay, so this is one of those examples where instead of doing the integration by parts twice to get your final answer, you can use the method of tabular integration because we have x to a power times either e to the something or sine of something or cosine of something. The something being a multiple of x. So here we can let u equal x squared, or dv is e to the negative x. We find all the derivatives of u down to 0. So the derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. And we find all the antiderivatives of e to the negative x. I will point out here, the antiderivative of e to the negative x happens to be the same as the derivative of e to the negative x. It's e to the negative x divided by -1, which is the same as e to the negative x multiplied by -1. So just be aware, right? We're anti-differentiating. It just happens to be the same as the derivative. So the antiderivative is negative e to the negative x. The antiderivative of that is positive e to the negative x. The antiderivative of that is negative e to the negative x. And then we have this pattern of plus x squared times e to the negative x minus 2x times e to the negative x plus 2 times negative e to the negative x. It's always plus minus plus minus plus minus, and it's always upper left to lower right. So then what we're going to say over here is this is equal to the limit as b goes to infinity of negative x squared times e to the negative x minus 2x times e to the negative x minus 2 times e to the negative x from 0 to b. And yeah, I didn't really think about this, but I feel like this problem is made much easier if you are able to recognize you can factor out an e to the negative x, which I think like I'm just kind of debating like which way do I want to show it to you. I won't do that, but I do think the thing we're about to do, you could do like in one step instead of two or three if you factor out the e to the negative x. But I'm not going to do it that way to show you because I feel like not everyone's going to think of that. So let's just plug in, but I am going to do something when I plug in. All right, this is the limit as b goes to infinity. Instead of negative b squared times e to the negative b, I'm going to write it as negative b squared over e to the positive b. And then we have minus 2b over e to the b minus 2 over e to the b. Now be careful here. When we plug in 0, we don't get just 0. We get 0 minus 2. I guess negative 0 minus 2. Be careful. It's really easy to convince yourself that plugging in 0 gives you 0 for all the things. Not the last thing. That's 2 times e to the 0, which is just 2. All right, so now, how about these limits? That's an infinity over an infinity. Well, I guess technically it's a negative infinity over infinity, but still it's an infinity over infinity type. And how do we take the limit of an infinity over infinity type? Good old L'Hopital's rule. Now here's the thing some people will say. Some people will say, and this is a convincing enough argument, this exponential function, e to the x or e to the b, is definitely going to overpower this polynomial function, this quadratic function. This limit should be 0. So should this, so should this. But technically, to show that work, you should be using L'Hopital's rule. So like for each of these pieces, like for this one, using L'Hopital's rule, you're getting the limit as b goes to infinity of negative 2b over e to the b, and then you do it again, and you get the limit as b goes to infinity of negative 2 over e to the b, which goes to 0. And then you can do that for that one. You don't have to do it for that one. So this one goes to 0. This one you use L'Hopital's rule. You get the limit as b goes to infinity of the derivative of 2b is, I guess negative 2b is negative 2 over the derivative of the b. That also goes to 0. So we get 0 minus 0 minus 0 minus negative 2. So we end up getting positive 2. I'll say one more thing. The reason I was mentioning that it might be helpful to factor out the e to the negative x is because if you write this part here, if you write this as just negative b squared minus 2b minus 2 all over e to the b, at least it's only one thing you have to use L'Hopital's rule for. You still have to use it twice, but it's kind of less messy than what I've written here. All right, that's improper integration.